Thanks for the invitation. So I'm from the Minerals Industry Safety and Health Centre at the University of Queensland. My colleagues and I have been looking at the human aspects of automation for probably about the last 10 years. So I'm not going to show you any pictures of equipment. I'm going to show you a bit about what automation looks like from the point of view of the people in the system, because it's important to realise that automation doesn't remove people from the system. It just changes the roles that they play. And for a system to be effective in doing what it needs to do, and to do it safely, it needs to be designed with taking people, the aptitudes, the capabilities of people into account. So this is a picture of a control room in Chile. We're looking at the screens, lots of screens. So the control room in this case is automated haulage, but it doesn't really matter what it is, in the sense that the dominant thing you'll see in all of these applications from the point of view of the people in the control rooms is the incredible array of information that they're presented with. So there's information received, decisions made, communication with the system, the IT system, but also the other people in the system who are out in the field. So it's a very busy, cognitively demanding situation. We'll come back to that in a minute. So and there's some examples, interfaces that are involved. On the left is a semi-autonomous dozer system. Now that photo was taken at the Convention Centre in Brisbane at the World Mining Congress. They had a setup with the dozers in operation on site in central Queensland. So very impressive technology. You'll see there we now have some interfaces that mimic the situation in the dozer, because it's a semi-autonomous system. On the right is the control room for autonomous drills. I particularly like the Xbox controller that's there for the occasion when there is teleop required. It's an interesting solution. Rather than mimicking the controls in the drill rig, let's change the interface to something that perhaps is more familiar to some of the newer generation. But the thing that does is that it introduces a new potential error, because to achieve the ability to control the different functions of the drill rig, there are 3 different modes that the controls operate in. And so once you've got different modes, then there's the potential for mode error. So on the left there is the control room at North Park's semi-autonomous underground loaders, and we're going to look at that situation in a little more detail later. On the right, underground longwall automation, very impressive. So removing people from the hazards, particularly underground hazards, that is the most effective way of improving safety and health. And I'd argue that is the way that the industry will achieve a step change. It's the only way. We've got to remove people from the hazards. And those situations there are both very effective at doing that. So I'm going to talk a little bit about some of the issues that have been encountered, but don't let nothing I say convince you that you shouldn't be going this way. This automation is the way to go forward to improve safety and health. So Australia is the gold medal winner for introduction of automation. There's no doubt, if you look at the number of installations or the number of vehicles, where there's Australia and then there's daylight. A lot of that was driven by Rio Tinto in about 10 years ago, and John McGarr was the director or the head of innovation at that time. So I've stolen a slide of his from a presentation that he gave about 10 years ago. It talks about his reflections on what was required to achieve the successful implementation of automation, and automated haulage in particular. So this is the slide that I stole. It's his personal reflections. So it's important, because if I say it's really critical that human factors is considered, you're going to say, well, you would say that. That's your profession. So this is John's summary: was underpinning the technology lies the critical world of the human. Safety is absolutely critical. If you don't get the safety right, then there's bound to be some problems. Listening to operators. So it's pointing to a human-centred design involving the people who do the work in the design. We'll come back to that again later too. Human systems interaction. Now, I think he actually meant human systems integration, and that's the final point that I'll come to in the presentation, is what that actually means, how you might go about that. Because it's a well-established set of principles that were developed in other industries, which I'll argue mining should be adopting. So you might say, well, yes, but what is the evidence that introducing automation has actually improved safety? And there is some. So now we have 10 years experience of automated haulage, and these are some data that were presented by Rio Tinto. The bar that I've circled on the left is near misses at surface mines which are manually operated trucks, and on the right, that's the autonomous haulage operations over roughly a 8-year period. So there's a dramatic difference in terms of the near misses that are reported. Now, one problem with those data is that the surface operations, the manually operated haulage tends to be in countries other than Australia, whereas the autonomous ones are in Australia. And Australia is the safest industry in the world. The statistics make that clear. So you could argue, oh, well, that's just a country difference. That's possible. However, if we look at other data provided by BHP, and these are all Australian operations now, the difference was also stark between the autonomous operations at Jimblebar and manual operations. So in terms here of events with fatal potential, there's a 75% difference. So we could quibble about the definitions, but the differences are so large that I'm happy to agree that the autonomous haulage has brought great safety benefits. However, it's not been without any incidents. So the Western Australia regulator does a good job of capturing incidents regardless of whether there are injuries or not. This is actually the most serious collision that's occurred with an autonomous vehicle. The green illustrates a manually operated water cart which was coming in the opposite direction on a haul road when the autonomous truck turned in front of it. It was an unusual place for the truck to turn. And so the water cart operator didn't notice until it was too late. Although the brakes were applied, the laws of physics apply, and there was a collision with minor injuries. Now, the interesting thing from human factors point of view is that there was a system provided within the water cart that was supposed to tell the operator what the autonomous truck was doing to help them maintain situation awareness, is the phrase that we would use. But the investigation suggests that, well, although there was this awareness system, the water cart operator wasn't fully aware. They lost situation awareness, is the term we'd use. So that's a design issue. And this is a photo taken from a light vehicle on a surface mine site in WA, with the lights that you can see coming towards us are an autonomous haul truck. Now, remember two things very much about this situation. One is that the driver said, oh, he's going to turn left. I'm thinking, well, that's no he, that's a computer. There's a lot of faith in that computer coming towards us. And then the other thing is I'm looking at the screen there thinking, well, how the hell did you interpret that screen and get that information? Now, obviously there's training and experience and all the rest of it, but from a human factors point of view, I'm going to say that's probably not the optimal interface design. And if we look at some of other examples of the interfaces that have been provided to help someone who's in a light vehicle or a water cart make decisions very quickly about whether they should stop or go, I'm going to say they're probably not the most effective interfaces, and that there's opportunity for improvement. Now, that's not an isolated case. There have been quite a few examples of incidents with no collisions, but close calls, where the bottom line was loss of situation awareness, and the screen wasn't effective in helping them to get it. There's just the top one there, so the operator used the mapping display to check on the location and misinterpreted the location of the truck. So the interface has not been effective in maintaining situation awareness. I particularly like the bottom one. So the investigation found the LV driver lost situation awareness, so they recognised that, having been distracted by focusing on the awareness screen. Well, hang on, that was the screen that was supposed to help them maintain situation awareness. So it's an example of how interface design is critical, and perhaps more information or more attention was involved. And the way to do that is through a user-centered design process involving the people who are going to use the screen, perhaps in a human-in-the-loop simulation situation, any number of ways that could be done. So closer to home, so this was a collision between a semi-autonomous dozer and an excavator. I'm not going to go through the scenario, I'm sure you're aware of it. The one thing I want to point out is that the control room operators were provided with lots of video feeds. One presumes that the reason for having a video feed like that is to allow the operator to maintain situation awareness. However, if you look at the bottom right there, those are the video feeds from the dozer that was about to have a collision. It's unsurprising that information wasn't able to be acted upon. So, because the bottom line is that if you're looking at a situation like this, just providing a video feed doesn't necessarily mean that that information can be used in time to prevent a collision. So providing visual information doesn't necessarily mean that the information can be used. So there's a few more steps required and needs to be thought through a bit more than that. Another example of things that can go wrong, this is again an extract from an incident report in WA. The schematic on the right is my interpretation of what the words say. So a light vehicle, the small box, drove through the intersection in front of a autonomous truck which was turning right. Now, site rules were they should have given way. So there's two possibilities there. One is that this was a particularly egregious example of loss of situation awareness, that they didn't notice the truck, was turning, and they drove through in front not being aware. The other possibility, and I think perhaps, or the thing that I want to highlight as another potential problem, is that becomes an overtrust situation. We have a lot of time spent training people and helping them understand the safety features of the autonomous vehicles to the point where, yeah, I trust it. In fact, I'm going to take advantage of the fact that I believe the truck will stop and I drive through an intersection in front of it. Because I'm important, I'm in a hurry, I've got to get to where I'm going. The fact that there was no recognition of that or reporting of it suggests to me that it was more likely an overtrust than loss of situation awareness. So this is another way in which systems can fail, and my concerns are things like if you put interlocked proximity awareness on underground vehicles, as there's a bit of a push to do, prevent collisions between pedestrians and vehicles underground. One potential consequence of that is that there'll be unintended consequences in terms of change of behaviour. If I'm a pedestrian and I now trust that the underground vehicles have interlocked systems and they'll stop for me, then that can change behaviour. So there's possibilities for other unintended consequences. So this was a little more complicated example where there was a loss of communication and the system safety features were enacted and the truck stopped. Pedestrians were dispatched to recover the trucks that had stopped, but that actually the loss of communication hadn't actually been with the trucks, it had been with another vehicle in the vicinity. And when that vehicle was turned off, suddenly communication was restored and the trucks were reactivated and started going off on their way again autonomously while people were nearby or in one case about to climb onto the truck. So it's an example of a sort of complex situation where the safety systems functioned, but there was some misunderstanding about what had actually gone on. So you could say it's a loss of situation awareness too, but the fundamental issue there was a communication disruption. So it's a matter of looking at the consequences of failures are not linear. If a system becomes complex, there are lots of different ways or consequences that can arise. So the analysis of the risks are not perhaps as simple as in the non-autonomous situation. So another credible failure mode is the overload of people in the control rooms. So we visited autonomous installations around the world in different places. So this again is in Chile. And we didn't spend long in any one place, but our observations were that in many cases the workload seemed overwhelming. There have been other researchers who've spent longer and were able to gather more detailed information. It's worth looking at some of those comments that have been made. It reinforced our view that in some cases the workloads were overwhelming. So the first quote there, it's constant churn, it doesn't stop, it's relentless. And Peter Chergwin described although the controllers had thought perhaps that autonomous operations might make their workload less, the experience was the opposite, and so that you've got cognitive load and communication responsibilities increased. And there were issues that could have perhaps been changed. So the bottom line here is that introducing automation or other new technologies needs to be taken into account very carefully the workload of the people involved. So that was a quick trip through some of the potential failure modes that we identified during our investigations. There are others there as well, and I'll give you a link to the white paper that describes all of those. But I want to leave that issues aside for the moment. That's one way of learning about lessons from automation, is to look at things that haven't gone perfectly well. But I want to turn now to another way of looking at things, and that's that font's gone strange. That's to investigate success. And so we did a case study a few years ago about the way in which North Parks were able to successfully implement semi-autonomous loaders. Now, the interesting thing here is this was the third attempt that the mine had undertaken. So it's not an easy task. It wasn't straightforward. And so we want to investigate success so that we've got a better chance of being able to replicate that in the future. So who was it I was talking to about what is a mechatronics engineer? What could a mechatronics engineer do on a mine site? I think it's the next speaker, that's right. Well, one of the things a mechatronics engineer can do is this, because the project manager here was Joe Cronin, who was a PhD in robotics. And that, I think, was one of the key issues. Now, the way this system works is that there are operators in the surface control room that they load the ore using teleop, and from then the loader autonomously travels to the dump point, dumps, and then returns to the next draw point without intervention. The operators in the control room are each responsible for 3 loaders. They've got a few screens, the joysticks that mimic the loader controls, and their job is to monitor the system status, but importantly, to make decisions in response to events that occur. So if a road deteriorates and we need to reduce the speed of the loader, the draw point hangs up, we need to change where the loaders are going. So they're still very much engaged. There's definitely improved safety. Joe's fond of saying there's never been an injury in an autonomous loader. And it's not that the hazards that the manual loader operators are exposed to are trivial. I mean, there's vibration, dust, noise, risks of running the bucket into the rib. One site I'm aware of was putting their loader operators in full face helmets, which I thought was probably not the best control measure. So the hazards that the operators are exposed to are non-trivial. Removing them is definitely a big safety benefit. But from the point of view of the site, there's also a large productivity improvement. Mostly that was from being able to continue to operate the loaders through blasting. So it's increased utilisation. So what does it look like? There's the picture of the control room. There's lots of attention to detail that's gone on to make that interface usable. So again, there's a case study I can point you to, but the highlights of that case study, the strategies for success, the first thing they did was to take everybody basically off-site and talk about what are the implications of the automation going to be. It turned out that pretty much everybody was going to be affected in some way. The other big or key thing that was that the designers of the system were on site, and there was a continuous feedback and rapid feedback loop between the operators and the designers, and things like changing the interface design in response to the operators' feedback was enabled very quickly. The interfaces had a very explicit intention about assisting and maintaining situation awareness, but there was also a role for the operators to utilise their flexibility, or provide flexibility in the interfaces so they could be adjusted by the operators, and empowering them to take action to change things. So not assuming that the engineers knew the best way to operate the system. And then there was some new possibilities that were unanticipated, which they were able to take advantage of. So that is, in a nutshell, sort of what human systems integration is about. But human systems integration is a well-defined component of systems engineering. The aim is to optimise all the human-related considerations. Now, the field is developed from the defence industry in response to some quite spectacular failures of the introduction of new technology. So automation technology that resulted in fratricide events, for example. People putting in the GPS location of their own, calling for fire to themselves, for example, the interface design errors. So this is the sort of requirement for acquisition program managers in the US Defence. We need to plan for and implement an HSI program to ensure the system is designed to be operated, but not just operated, maintained and supported by all the people in the system, not just those who operate it. Now, the design of human systems integration for defence it's bigger than Ben-Hur. The documentation is quite immense, and it's, I think, probably more complicated than what is required in mining. But there are other versions, so NASA have some very good documentation. Again, space is perhaps a little more complicated than mining, maybe. Certainly their documentation is complex. Another big user is rail. And so now we're getting closer. And in fact, the robot on the right, the biggest robot in the world, again, is Rio's autonomous heavy haul train. So now we're getting closer to mining. Now, in Australia, we don't have huge defence or space industries. In Australia, the biggest employer of human factors professionals doing human systems integration is actually rail. Any rail operator that wants to put in a new technology has very rigorous requirements for including human systems integration. And that's, of course, understandable. We've got huge public safety issues. And there is a national regulation for rail safety. It's harmonised. I didn't realise this until recently. So rail regulations are harmonised. Although they're state legislation, they're all the same. But includes in that a statement about what's required in a safety management system includes human factors. So procedures for the integration of human factors, principles and knowledge into all relevant aspects of operational and business systems. So my suggestion is really this is what mining regulations should also say. May not be popular, but to me that is the sort of language that we should be, or the sort of aims that we should have in mining as well. So I've attempted to recast the principles of human systems integration that are relevant to mining in this figure. So the first thing to realise is that it's not we do it once. Each of the domains and the aspects need to be addressed throughout the whole systems engineering cycle, starting with requirements through design and development and then to testing and evaluation. So it's not something that happens once. The domains we're talking about, we start with staffing. So where are people going to be involved in the system? And then the next thing you might say is, well, who are those people going to be? What experience do they already have? Because that will impact on the extent and the nature of training that we need to provide. And importantly, the other aspect there is how do we determine competence and how do we maintain competence? The human factors engineering, well, that's the bit about the design of interfaces, the design of decision support, how we're going to communicate with each other, how we're going to maintain situation awareness, both of individuals but also of the collective, what you might call distributed situation awareness. So human in the loop simulation is a great sort of set of tools here. Safety is a subset of human systems integration. All your safety analyses have to take people into account. If there's no people involved, it's not safety. It might be loss mitigation or something, but it has to take people into account. Some of the techniques will be familiar, but others might not. So systems theoretic process analysis, for example, is a technique, comes out of software safety, trying to understand how things can go wrong, but treating it as a control problem, not as a fault problem. Then the last one is the health aspects, and here we might think about things like the health consequences of overload on the system. Now, again, as I said, talking about a whole system, multiple points through the whole systems engineering process. Another way of looking at this is that what we're trying to achieve is human readiness levels that match technology readiness levels. So the system not only has to be ready in a technology sense, it also has to be ready to be used. So the take-home message is that any technology implementation, not just automation, needs a human systems integration plan. We need to know how people are going to be considered during the design. And it's not something that the vendor can do alone. It has to be done in conjunction with the purchaser. So we need a plan to work out how that's going to happen. I said I'll give you a link to a white paper. So that white paper has more details, particularly about the credible failure modes, but also about human systems integration and its implementation. Thank you.